The things that we've seen so far, the techniques that we have for solving linear and quadratic equations, will allow us to solve any equations of those forms. But of course, there are lots of other kinds of equations out there. Now, unfortunately, we aren't going to be able to have a general strategy that's going to work with all of them. However, we can use a lot of the same techniques that we used for those, such as the zero-factor theorem, to solve even more complex problems if we do it in a sufficiently clever way. So we're going to see a few examples of this. We're going to see how to handle equations involving square roots and cube roots and so forth and so on. And we're going to see how to handle problems that don't immediately look like they are quadratic, but actually are. So let's go ahead and get started. So sometimes we can just factor, and there are a few different ways that we can do that. So let's look at what happens with the following polynomial. Let's look at the polynomial 6x cubed minus 3x squared minus 3x equals 0. Let's look at this equation right here. Now, this is not a quadratic equation. This has a degree 3 polynomial in it. This is what's called a cubic equation. And while there is a cubic formula, like there is a quadratic formula, it is very complex and really not worth memorizing. However, this cubic equation, as well as others like it, can actually be solved using our techniques of factoring and using the zero-factor theorem. The trick is to remember that our first step when factoring is always to factor out the greatest common factor, GCF. And that means that we want to start off by looking at all the terms in our problem, in our polynomial, and say what's common to all of them and factor that out first to simplify the problem. So let's do that here. Let's look at the polynomial on the left-hand side of this equation and say, what can we factor out of this? Well, we can certainly factor a 3 out. A 3 is a common factor of all of the coefficients in this problem. But notice we can also factor an x out. Each one of the terms involved has an x in it, and that's what's really going to make this problem work for us. We can factor out an x, and let's see what we have left. When we factor 3x out of the polynomial above, we get a 2x squared left in the first term, minus x in the second term, and then minus 1 in the last term, equals 0. Now we could go ahead and use the zero-factor theorem here, but we're actually going to go one step further and use a slightly more sophisticated version of it. From this point, we can continue factoring actually, and we can try seeing whether we can factor this, this term inside, this polynomial inside, I should say. And once again, it's going to turn out we can factor this polynomial as 2x plus 1 times x minus 1 equals 0. And so what we've done is we've factored completely. And now we can use the zero-factor theorem with all 3 of these factors now. We have 3 expressions multiplying together to equal 0. And if we have 3 factors multiplying together to equal 0, well then one of them has to be 0. At least one of them has to be 0, just like with the zero-factor theorem before. So this means that 3x equals 0, or 2x plus 1 equals 0, or x minus 1 equals 0. Whenever we have any number of things multiplying together to equal 0, we know that one of them has to be 0. And so we can solve each one of these to get x is equal to 0, or subtract 1 from both sides, get 2x equals -1, divide both sides by 2, get x equals -1/2, or we could get x equals 1. So in this case, we were able to use the zero factor theorem with factoring to get 3 solutions to this equation. And this is correct. So our solution here, our solution set, is 0, -1/2, and 1. This equation actually has 3 solutions to it. Now, you'll notice that when we worked with quadratic equations, degree 2 polynomials, we got 2 solutions out of it most of the time. Sometimes fewer, but never more than 2. And here, with a degree 3 polynomial, we've gotten 3 solutions out of it. Turns out this isn't an accident. If you have a degree n polynomial, where n is any positive integer, then it will have, at most, n different solutions. And so, the fact that we got 3 different solutions out of a degree 3 polynomial here isn't surprising. It's, in fact, sort of what we expect. Now, sometimes this second step that we did, where we factor the remaining expression inside, doesn't work. So let's look at an example of that. Let's look at x cubed plus x squared plus 6x equals 0. A fairly simple equation. But let's go ahead and factor an x out of the left. Let's go ahead and continue with the process that we had before. Getting 0 on one side and factoring is going to be key to a lot of the strategies that we have. So we get x times x squared plus x plus 6 equals 0. Well, now we're done factoring, because this term, this second term, x squared plus x plus 6, this doesn't factor. So that means that we use the zero factor theorem now. We factor as far as we can, then we use the zero factor theorem. This means that x equals 0, or x squared plus x plus 6 equals 0. Well, the x equals 0 solution, we understand that. That's fine. We don't need to do any more work on that. But x squared plus x plus 6 equals 0 is a new equation which we want to solve. Now, this is a good time to take a step aside and do some work over on the side. Let's handle x squared plus x plus 6 equals 0 by itself. For a second, let's ignore where it came from. We just want to find the solutions to this equation. And we can ignore everything that came before, take this one little chunk and treat it as if it was its own little problem, and say we want to solve it. So we go and we look at it and we say, well, we'd like to factor it, but we can't. In fact, we already know we can't, because that's why we're here. So we move to the quadratic formula. So the quadratic formula will tell us that the solutions to this equation are x is equal to -b, b in this case is 1, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And simplifying all this down, we get -1 plus or minus the square root of, now this is going to be 1 squared, which is 1, minus 4 times 1 times 6. 4 times 1 times 6 is 24, and 1 minus 24 is -23. And then the denominator is just 2. So we get negative 1 plus or minus the square root of negative 23. The only way we have of writing that any simpler is to write it as the square root of 23i. And so that's what we're going to have to do. So these are the two solutions to the equation x squared plus x plus 6 equals 0. So that means that back in our original line of reasoning, instead of saying x squared plus x plus 6 equals 0, we can write x is equal to negative 1 plus or minus the square root of 23i all over 2. And here are our, again, 3 solutions. And the solution set that we have consists of 0, negative 1 plus the square root of 23i over 2, and negative 1 minus the square root of 23i over 2. So we see that in this case we have one real solution of 0, two complex solutions, negative 1 plus square root of 23i over 2, and negative 1 minus square root of 23i over 2. And we're done. These are the solutions to the original problem. So as long as you can factor out a common factor from your degree 3 polynomial, you can use this process. Now, this process doesn't necessarily work on degree 4 polynomials, and it doesn't necessarily work if the degree 3 polynomial doesn't have a common factor in it, but it is something that happens sometimes, so it's another tool in your tool belt. Let's take another example. We can look at the equation x cubed plus 5x squared minus 4x minus 20 equals 0. So here's another cubic equation. It's got a degree 3 polynomial on one side, 0 on the other. It's again in standard form. But we can't handle this the same way we did the previous ones. There is no common factor here. There's nothing that you can factor out of all of the terms of this polynomial, and so the previous technique won't work. Now, when you're in a case like this, you can always try a technique called factoring by grouping. I should say we will try factoring by grouping. It will sometimes work. Frankly, it often won't. But if you're stuck and you're not sure where to go, factoring by grouping is a way to go. So the way this works is we're going to look at the first two terms together and the second two terms together. And in each case, we're going to factor out the greatest common factor just of those two terms. So let's look at the two terms in the red bracket, x cubed and 5x squared. And we'll look and we say, what's the greatest common factor of these two? We have no common numbers that we can pull out, but we can pull out an x squared. And we can factor an x squared out of this first pair of terms here. So we can get an x squared and x plus 5. And now we can say, all right, well, what do we factor out of the two things in the blue bracket? And notice that I've included the negative in front of the 4 with the blue bracket. This is very important. Remember, always negative numbers attach, or negatives attached to the numbers to their right. They have to go along with them. So here we want to factor the greatest common factor out of the two terms in the blue bracket. We can see that we can factor a 4 out. 4 is the greatest common factor of those two. Now, in fact, we want to be a little bit more careful. We actually want to factor out a negative 4 because we always want to make sure to make the first term, or the first coefficient, I should say, positive. So because we had a negative 4 in our first term here, we want to factor out a negative whatever our greatest common factor is. In this case, our greatest common factor happens to be 4, so we're going to factor a negative 4 out. So what that does is it pulls a negative 4 out of each of the terms in the blue bracket, or in other words, divides them by 4. So we get x, and then factoring a negative 4 out of negative 20 gives us a plus 5. So this first step, we just randomly grabbed the first two terms together, pulled out the greatest common factor, grabbed the second two terms, pulled out the greatest common factor, and here's the point where you check to see whether factoring by grouping will happen to work or not. What we do now is we compare the two expressions that we have left after we factored out the greatest common factor. And we say, are they the same? Are they exactly the same? If so, then factoring by grouping works. We have a win. So if they're equal, we can factor this expression out of the whole side, the whole left-hand side here. So we can take the x plus 5 that's common to both parts of the left-hand side of the equation now, and write it as x plus 5 times, and then we see what's left. Well, in the first expression, we had an x squared times an x plus 5, which leaves an x squared behind. And in the second term, we had a negative 4 times the x plus 5, which means that a negative 4 gets left behind after we factor out the x plus 5. So we've managed to factor by grouping. We get x plus 5 times, now I'll go ahead and simplify this, x squared minus 4 equals 0. Now we want to continue factoring. In this case, we can actually continue to factor. X squared minus 4 is a difference of squares, so we know how to factor that actually. X squared minus 4 is x plus 2 times x minus 2. Now if that hadn't happened to be the case, then we would have needed to either use the quadratic formula or use our square root, the square root theorem in order to get our answers, but we factored and made it work. So now, by the zero factor theorem, we have three terms, x plus 5, x plus 2, x minus 2, that are all multiplying together to give you 0. That means that one of them had to be 0 to begin with. X plus 5 equals 0, or x plus 2 equals 0, or x minus 2 equals 0. And we can take each of these equations and solve them for x. So x is equal to negative 5, or x is equal to negative 2, or x is equal to positive 2. So there's our solution. Our solution set is the set negative 5, negative 2, 2. And again, we see we have three solutions to this degree 3 polynomial equation. Now, the question is, what would happen if we went through the first two steps of this process, but then when we got to this one, we didn't have the same expression, that these x plus 5 expressions weren't the same? Well, then we'd be stuck. That would mean that factoring by grouping just doesn't work for this problem, and you'd need to try to find something else. So factoring by grouping is something that you can try, but it is sort of a long shot. It's something that's not going to happen all the time, but it's something to try when you've exhausted other methods, other ways to solve things.